The more recent data are again completely consistent with all of this. Again, this is a technical picture, but just admire it and say, oh my God, isn't that wonderful? What you see here is these predictions are tying in beautifully with the expectations of what in many ways is the simplest possible model we could have of the origin of structure. But we also get out of this estimates of the various components of the universe. And here is the killer diagram. What it's showing us is that these beautiful observations show that only 21% of the matter in the universe is dark matter. Here's us, 4% of ordinary matter like you and me. But most of the inertial mass in the universe is in the form of this dark energy. That's very hard. That's a very, very hard problem. And the reason is the effects only become observable on the scale of the universe itself. You see, because of the peculiar behavior upon scale, it turns out that whereas ordinary gravity you can deal with locally, this stuff only appears on the very largest scales. And so the experiments that we're looking at doing are very, very difficult indeed. Again, the people in Edinburgh have been deeply involved in a wonderful European Space Agency mission to understand the properties of that, and let's hope that all works. But the other wonderful thing is that in addition to that experiment, we've got all of these different ways of estimating cosmological parameters, and I won't run through them, except to note that for the first time in the history of cosmology, everybody agrees. This has never happened before. Never, ever happened before. But it means every time you do these analyses, you find exactly the same answers. So we're pretty confident we're along the right lines. And therefore, it enables us to do better experiments to understand in more detail the origins of these structures in the universe. So, with all this great success, what's the problem? Why worry? Why are you still in business? Well, the answer is there's lots of very fundamental problems that these raise. For example, we need to understand why the universe is the same in all directions, why it's homogeneous, why it's baryon-less, why we're made of matter and antimatter, why the cosmological parameters have their observed values, and where the initial power spectrum came from that made the structures that we see. Here are 5 solutions. That's just the way the universe is. That's the way it was set up. That's not a very good solution at all, because you just say that's how it works. But it might be just too difficult for us to understand how to do it. The second one is the anthropic cosmological principle, which says that we could only have life in certain classes of universe. This is what's called intelligent life. That means you and me. That it takes a certain long time to form intelligent life, and therefore that must set constraints on the type of universe you live in. Then there's the inflationary scenario for the early universe, which I'll say just a moment about in a moment. Use particle physics to understand the early phases of the universe, and then almost certainly the real answer is here, something else we have not thought of, and that would certainly involve new physical concepts. This is what I call the Donald Rumsfeld cosmological model. It's the unknown unknowns, the things that we don't know. And almost certainly that's the answer to all of these questions. There's something missing from the models that we have at the moment. But this inflation picture can do a lot for us. For example, the standard Big Bang has got a scale which expands like this and a temperature which decreases like this, and you only get a factor of 10 to the 31 from the earliest phases to the present time. And that's not good enough to make the universe isotropic and homogeneous. But if you put in an inflationary phase here, between, say, 10 to the minus 34 of the second, 10 to the minus 32 of the second, then you can have an exponential expansion, which gives you an extra factor of 3 times 10 to the 43, so that you expand the universe by 3 times 10 to the 74, and that's a very good number. Because then you make everything wash out on a scale far beyond the scale of our observable universe. Now, that is very good. It solves several of the problems, but there's one even more amazing thing that happens. And that is that there's a property of these types of models which was not at all expected. And that is, you need to think about the fluctuations that occur in these quantum fields which drive these. And you can work out what the spectrum can be. Amazingly, in the simplest model of inflation, the fluctuations in these fields result in exactly the spectrum we need to explain the structures we see in the universe today. Nobody could have predicted that one. That's very deep. I can actually derive it on the back of an envelope using first year physics, but I'm not going to do that because I don't know that. We're running out of time. But the important thing, this is very encouraging. Although the details are not known yet, what it's telling us, we've at least got the beginnings of a theory which enables us to understand many of these very deep and difficult problems. We're still left with this terrible business. What exactly is the nature of the dark energy? And that's going to hang over us for some time. And here's the words, just to finish up, from Little and Life in their book, Cosmological Inflation and Large-Scale Structure. It's what I've said already, but it's rather nicely phrased. Although introduced to resolve problems associated with the initial conditions needed for the Big Bang cosmology, inflation's lasting prominence is owed to a property discovered soon after its introduction. It provides a possible explanation for the initial inhomogeneities in the universe that are believed to have led to all the structures we see, from the earliest objects formed to the clustering of galaxies to observed irregularities in the microwave background. And that is significant progress. Do keep an eye open for what will happen over the next little while. The Planck satellite will be publishing its results, and I believe some people in this room may know some results already, but they won't tell us because it's all embargoed until everything comes out. But that will give us an order of magnitude improvement on all these analyses. And finally, just to summarize, the future, the progress of the last 15 years has been absolutely staggering. When I started doing cosmology in 1963, if we knew anything within a factor of 100, we thought we were being very, very clever. Now we're talking about precision cosmology. We were trying to actually understand the detailed physics of what happened very, very early. And these problems are exercising the imaginations of the very best astrophysicists and cosmologists, many of whom are in this room this evening. The solution of these deep problems promises to bring new understanding of the laws of physics which have determined the origin and evolution of our universe. Thank you.